testing for linear independence. Determine whether the set of vectors in P2 is linearly independent or linearly dependent. So we have this set S consisting of 2 minus x, which we'll call our first vector v sub 1, 2x minus x squared, which we'll call our second vector v sub 2, and 6 minus 5x plus x squared, which we'll call our third vector v sub 3. So to test whether these are linearly independent or linearly dependent, what we'll do is we know that if we set up the equation c sub 1 times v sub 1 plus c sub 2 times v sub 2 plus c sub 3 times v sub 3 equals 0, where c sub 1, c sub 2, and c sub 3 are constants, then if there's a trivial solution, then we'll have something independent. If we have a non-trivial solution, we'll have something that's linearly independent. So what we'll do is we'll take c sub 1 times v sub 1, 2 minus x, plus c sub 2 times v sub 2, 2x minus x squared, plus c sub 3 times v sub 3, 6 minus 5x plus x squared, and that will have to be equal to 0. Well, when we expand this, the c sub 1 times the 2 minus x will give 2 times c sub 1 minus c sub 1 times x. C sub 2 times the 2x minus x squared, that will give us plus 2 c sub 2x minus c sub 2x squared. And when we multiply the c sub 3 by the 6 minus 5x plus x squared, we'll wind up with 6c sub 3 minus 5c sub 3x plus c sub 3 times x squared, and that will all be equal to 0. So we'll first group together the constant terms. We'll have 2 times c sub 1 plus 6 times c sub 3. And then we'll group together the first degree terms. We'll have negative c sub 1x plus 2c sub 2x, and then minus 5c sub 3x. And then finally, the second degree terms, we'll group those together. We'll have minus c sub 2x squared plus c sub 3x squared, and that will be equal to 0. And so then we'll set up equations. Since everything has to be 0, then all of the constant terms will have to be 0. So 2 times c sub 1, and there's no c sub 2, so we'll add 0 c sub 2 plus the 6 c sub 3, that will have to be 0. And then the first degree terms, those will have to add to 0. So negative c sub 1 plus 2 c sub 2 minus 5 c sub 3, that will be equal to 0. And then for the second degree terms, the same thing. There is nothing involving c sub 1, so we'll have just 0 c sub 1. And then we'll have minus c sub 2 plus c sub 3, and that will all be equal to 0. And then we can set up an augmented matrix. So the first row will consist of 2, 0, and 6, and then we'll have a 0. The second row will consist of negative 1, 2, negative 5, and then 0. And then third row will consist of 0, negative 1, 1, and then of course 0. And we'll draw a line here to separate that last row. So what we could do first is we could try to eliminate the first term from this second row. So what we'll do to do that, we'll take 2 times the second row and add the first row. And when we do that, of course, the first row will stay the same. But then the second row, that will become negative 2 plus 2, which is 0, and then 4 plus 0, which is 4, and then negative 10 plus 6, that will give us negative 4, and of course we'll just get 0 on the right-hand side. Then of course we'll have 0, negative 1, 1 in the last row. And then what we can do is if we take 4 times the third row and add the second row, what will happen is, well, our first row stays the same, our second row stays the same, but our third row, when we do that, it's going to become all zeros. So here we see that we don't have anything that's non-zero. So we can see that we're going to have no unique solution. So there will be no unique solution, but we'll have to determine if there's a non-trivial solution. So we saw that for our test to determine whether we're linearly independent or linearly dependent, we solved this equation and we got an augmented matrix, and we got to this point using elimination. We saw that we had no unique solution. But if we only have a trivial solution, then of course we could say that we're linearly independent. But here, let's suppose we say that C sub 3 is equal to 1. Well, if C sub 3 is equal to 1, then we can plug it into this equation here, 4C sub 2 plus negative 4C sub 3 equal to 0. And we'll get 4C sub 2 minus 4 equal to 0. And that will tell us that C sub 2 is equal to 1. And then if that's the case, well, then we'll use this top equation where we have 2C sub 1 plus 0C sub 2 plus 6C sub 3 equal to 0. So we'll get 2C sub 1 plus 0 plus 6 times 1 equal to 0. And that will give us 2C sub 1 equal to negative 6, or C sub 1 equal to negative 3. So here we find that C sub 1 is negative 3, C sub 2 can be 1, and C sub 3 will also be 1. So here we have a non-trivial solution. And so if we get a non-trivial solution, that tells us that we're going to have something that's linearly dependent. So our vectors in this case are going to be linearly dependent because we're able to get a non-trivial solution to this equation, C sub 1 v sub 1 plus C sub 2 v sub 2 plus C sub 3 v sub 3 equal to 0. Testing for linear independence. Determine whether the set of vectors in M sub 2 comma 2, set of all 2 by 2 matrices, is linearly independent or linearly dependent. So we have the matrix A, which we'll consider our first vector v sub 1, consisting of 1, 0, 0, and negative 2. The matrix B, which we'll consider our second vector v sub 2, consisting of 0, 1, 1, and 0. And then we'll have the matrix C, which we'll call our vectors v sub 3, consisting of negative 2, 1, 1, and 4. Now our test for linear independence says that if we take C sub 1, where C sub 1 is a constant times the vector v sub 1, plus a constant C sub 2 times the vector v sub 2, plus a constant C sub 3 times the vector v sub 3, if we set that equal to 0, if we get only a trivial solution, then we'll be linearly independent. But if it's possible to get a non-trivial solution, then we'll be linearly dependent. So what we'll do is we'll set this up. We'll take C sub 1 times the first matrix, 1, 0, 0, negative 2, and then we'll add C sub 2 times the second matrix, 0, 1, 1, and 0, and then we'll add C sub 3 times the third matrix, negative 2, 1, 1, and 4, and that will have to be equal to the 0 matrix, consisting of all zeros. And so when we multiply by the constants and combine, we'll wind up with the following matrix. The entry in the first row and first column will be C sub 1 minus 2 times C sub 3. The entry in the first row and second column, that will be C sub 2 plus C sub 3. And then the entry in the second row and first column, that will be C sub 2 plus C sub 3. And for the second row and second column, we'll get negative 2 times C sub 1 plus 4 times C sub 3. And of course, that will be equal to the matrix consisting of all zeros. So if we set the corresponding entries equal to each other, we'll get 4 equations. We'll get C sub 1 minus 2C sub 3 equal to 0. C sub 2 plus C sub 3 equals 0. Once again, C sub 2 plus C sub 3 equals 0. And finally, negative 2 times C sub 1 plus 4 times C sub 3 is equal to 0. Now we can note that C sub 2 plus C sub 3, that's repeated, so we only need to use that once. So we'll have C sub 2 plus C sub 3 equal to 0. And negative 2c sub 1 plus 4c sub 3 equal to 0, that's a multiple of the first equation. So we only need that first equation, c sub 1 minus 2c sub 3 equal to 0. Now it appears that this could have infinitely many solutions. And what we could do is we could come up with one solution. Let's just suppose that we let c sub 3 equal to 1. Well, if c sub 3 is equal to 1, we can plug that into the first equation and get c sub 2 plus 1 equal to 0, meaning c sub 2 will be equal to negative 1. And then if we plug c sub 3 into the second equation, we'll get c sub 1 minus 2 equal to 0, giving us c sub 1 equal to 2. So here we get c sub 1 equal to 2, c sub 2 equal to negative 1, and c sub 3 equal to 1, which tells us that we have a non-trivial solution. And if we have a non-trivial solution to this equation that we use for our test for independence, that tells us that our set of vectors is going to be linearly dependent. So our vectors are linearly dependent because we have a non-trivial solution to this equation that we use as a test for independence. Spanning sets. Determine whether the set S equal to the set containing 1, comma x squared, comma 2 plus x squared spans P2, the set of all second degree polynomials. So we can think of each of these members of the set as a vector. So we can have v sub 1 for this 1, v sub 2 for the x squared, and v sub 3 for 2 plus x squared. So we want to know if we can take some linear combination of these. Let's say c sub 1 times v sub 1 plus c sub 2 times v sub 2 plus c sub 3 times v sub 3, where c sub 1, c sub 2, and c sub 3 are constants. And if we can use those to get all possible second degree polynomials. So we could try to pick a specific second degree polynomial. Let's say x squared plus x plus 1. And one thing we can also note is that the third vector is just a linear combination of the first two. If we take 2 times v sub 1 and add v sub 2, we'll get 2 times 1 plus x squared, giving us 2 plus x squared, telling us that the c sub 3 will be 0. We don't need to use that one because the 1 and the x squared can create that third vector. So we'll just have c sub 1 times v sub 1 plus c sub 2 times v sub 2 equal to x squared plus x plus 1. So we'll have c sub 1 times 1 plus c sub 2 times x squared equal to x squared plus x plus 1. So that will give us c sub 1 plus c sub 2 times x squared equal to x squared plus x plus 1. So we can see that c sub 1 will be equal to the constant term. C sub 1 will be equal to 1. And c sub 2 will be equal to the coefficient of x squared on the right-hand side. So c sub 2 will be equal to 1. But then we can see that from these two vectors, we don't have anything involving x. So there's no way to create this polynomial using a linear combination of the vectors v sub 1 and v sub 2, because none of the vectors have x, which is going to be necessary in order to span P2. So in this case, we're going to have to say that S does not span P2. And it doesn't span P2 because none of the vectors contain the x term necessary to span P2. Explaining why a set is not a basis. Explain why S is not a basis for P2, the set of all second degree polynomials, where S is equal to, well, we'll have the first vector be this polynomial 1 minus x, that will be v sub 1, and then 1 minus x squared will be v sub 2, and negative 1 minus 2x plus 3x squared, that will be our third vector, v sub 3. And let's look at what constitutes a basis. So we see that in order for S to be a basis for P2, it will have to span P2 and also be linearly independent. So we'll look at the second condition first. If we take 2 times the first vector, v sub 1, and then we subtract 3 times the second vector, v sub 2, we're going to get negative 1 minus 2x plus 3x squared. So we see that 2 times v sub 1 minus 3 times v sub 2 is equal to v sub 3. So this tells us that S is not linearly independent. So we violated the second condition. But we can also check the first condition. Now, what we could do is if S is going to span V, that means we can take constant multiples of the 3 vectors to get any polynomial in P2. So for example, we could take a constant C sub 1 times the first vector, 1 minus x, plus a constant C sub 2 times the second vector, 1 minus x squared, plus a constant C sub 3 times the third vector, negative 1 minus 2x plus 3x squared. And that could give us any polynomial in P2, for example, x squared plus x plus 1. So from this equation, we can get a system where we'll get C sub 1 plus C sub 2 minus C sub 3 equal to 1. And then negative C sub 1 plus 0 C sub 2 minus 2 C sub 3 equal to 1. And then 0 C sub 1 minus C sub 2 plus 3 C sub 3 equal to 1. And of course, we get this just by expanding the left-hand side and setting the second degree, first degree, and constant terms equal to each other. So from this system, we can get an augmented matrix. We'll get the augmented matrix with the first row 1, 1, negative 1, and 1. The second row, negative 1, 0, negative 2, and 1. And the third row, 0, negative 1, 3, and 1. And using elimination, we eventually get to the matrix with the first row 1, 1, negative 1, and 1, then 0, 1, negative 3, and 2, and then 0, 0, 0, and 3. And we can see from this last row, we get a contradiction. We get that 0 is equal to 3, but that's not the case. So this is a contradiction, which tells us that this system is trying to do something that's not possible. Meaning that it's not possible for us to get this polynomial x squared plus x plus 1 from these 3 polynomials in S. So in this case, S does not span P2. So in this case, we're not going to have a basis. So S is not a basis for P2 because it does not span P2 and it's not linearly independent. Explaining why a set is not a basis. Explain why S is not a basis for M sub 2 comma 2, the set of all 2 by 2 matrices. So we have S, which consists of one matrix with the first row 1 and 0, the second row 0 and 1. We'll consider that our first vector v sub 1. And our second vector v sub 2 will be the second matrix with first row 0 and 1, second row 1 and 0. So let's look at what constitutes a basis. So in order for S to be a basis for M sub 2 comma 2, it will have to span that space and also be linearly independent. So we'll first take a look at the second condition. We can see that there's no way to take a constant C sub 1 and multiply it by the first vector to get the second vector, because we'll get C sub 1 and 0 in the first row and 0 and C sub 1 in the second row. And if we set that equal to the second matrix, 0 and 1 in the first row and 1 and 0 in the second row, we get something that's not possible. So this is not possible. So this means that S is linearly independent. So one vector or matrix is not a constant multiple of the other. But for the first condition, S spans V, if S spans V, this space of all 2 by 2 matrices, well, that means that we can create any 2 by 2 matrix from these 2 matrices, meaning we can take a constant multiple C sub 1 of the first matrix, 1, 0, 0, and 1, and add a constant multiple C sub 2 of the second matrix, consisting of 0, 1, 1, and 0, and we can get any matrix that's a 2 by 2 matrix. For example, the matrix with the first row 1 and 0 and the second row 1 and 0. Well, if we set this up, what will happen is when we add the two matrices, we'll get C sub 1 in the first row, first column, and in the first row and second column, we'll get C sub 2, and in the second row and first column, we'll get C sub 2, and in the second row and second column, we'll get C sub 1. And that will have to be equal to this matrix consisting of 1 and 0 in the first row and 1 and 0 in the second row. Well, from this equation, we'll see that C sub 1 will be equal to 1, and C sub 2 will be equal to 0. We get that from the first row, but from the second row, we see that C sub 2 is equal to 1, and C sub 1 is equal to 0. So C sub 1 and C sub 2 cannot take on multiple values. So in this case, this means that we have no solution, meaning it's not possible for us to get this matrix from the two matrices in S. So in this case, we can see that S does not span this space of all 2 by 2 matrices. So in this case, we see that S is not a basis for M sub 2 comma 2 because it does not span that space and it's not linearly dependent.